So this video is going to show you how to work with the state machine in Lab07. So this is a template. It's provided on my website for the Lab07 step-by-step tutorial. Okay, you can directly click that link and find out this exactly the same code. Okay, no difference. And and you can see that the state machine for the UR2 is already given. Okay, I'm not taking out anything over here. And this will be helpful for Lab 6 as well. If you are still having trouble with Lab 6, you can definitely refer to the Lab 7's the ISR for UR2 and try to put it there and see if that works. Okay, but now Lab 7 has a new task. Okay, so it's trying to put the transmission, all the steps of transmission into ISR as well. So that's the major difference compared to Lab 6. I still have a Lab 6 code over here, but I can see whenever S is being pressed, it's actually keep calling a function, to do it in the while loop. But here in Lab 7, it's everything here in transmission is being handled by ISR. Okay, they can do the same thing, but usually ISR is getting better controlled with all the different states with less errors. It's just because it's definitely getting timed by the timer. It gets into it and follows a certain states. It's not getting confused by itself. It's always accurate. So I don't have too many things for you to fill in, but you can see for each state there will be like a few lines of code that you have to put in. So this recorded video's goal is to go through the diagram of the state machine, and I will write down the code on the paper. So hopefully you can create the C code from whatever is being covered today in the lecture. Okay. So first, you can imagine that whenever the way Lab 7 works is whenever a customer or user press S, and it's gonna turn this flag to be true. All right. So the reason for that is because the interrupt, whenever the timer's on, right? So it's gonna get into the interrupt after the timer's after the timer's up. So it's not being controlled by anything else. It doesn't like the UART, right? So if there's nothing being received by the receiving buffer, it won't interrupt. However, the timer is different. The timer, whenever you turn it on, powered up, it's gonna start running. Okay, so it's gonna get into this interrupt with a certain period of time, for sure. So the only way that I can control it is to turn on the flag, right? So that's why we have S. Whenever you press S, the microcontroller knows that you want to transmit whatever being saved in the transmit buffer to IR, the IR transmitter. Okay, so firstly in here you see the flag, right? So you see the flag. It's called transmit start, right? So you know that if you want to get out from this idle state, because every time there's no other controls, you can see there's nothing. They're just declarations. It's a switch case statement, so there's no other control. But however, because the initial state is idle, that's why it's going to stay in this idle state forever, unless that flag is true. So in that case, this if statement over here has to be transmit start to be true. Okay, so it won't just skipping, get into here, it's idle state, yes, but however it doesn't satisfy, then just break, right? So it just quit that timer. You can see at the bottom there's it breaks and then it reaches here, so set up the timer, it's timing, right? Start timing until it overflows again. It's gonna come back and then to this idle state if you don't turn on the flag. Okay, so now it's like a door, right? It's a door that controls the entrance to all the other states, because at the very beginning it stays at the idle state. So in that case, we can draw the state machine diagram in the following way. So I'm going to show you really quick how we do that. Okay. So definitely first, the first state you want to draw on the paper is going to be idle state, right? Idle. And you need a flag. It's called transmit start. If it's false, right, just keep looping to itself. If it becomes true, move to the next state. So for the next state, we are doing TX. You'll see why we have to do that. Okay, TX I highly recommend that you program the state machine by yourself, since you know sometimes you want to put the parameters or assigning values to some variables in a different state, because every time it enters it, you don't want to reset it anymore. That's why we have a extra state over here to hold the mask variable. So in this start bit, definitely you know that as a start bit, because for UART, you need a logic 0. Remember the UART logic? You need to pull it down first, right? And then send data, and then pull it up. So this is a start bit, and this is a stop bit. Okay, so first you need to do the LED on, right? Why LED on? Since you need this stop bit. When LED is on, it's a PWM, right? That function. I'm not writing the full name of the function, but you can find it. We have used it for millions of times. So if you do the LED on, it's outputting a PWM, right? And then the PWM is going to be decoded as a logic 0. Okay, remember? So, and logic 0 will be decoded as logic 1. That's how the decoder works. So if you want to give a 0 for the UART, you have to turn the LED on. Okay, turn the LED on. Turn the PWM's LED on. That's how the decoder works. So that's the start bit. So first you want to turn it on, right? That's the first step. And the second step, definitely next time when it comes to here, you don't want to keep staying in this state forever. You want to transmit to the transfer to the other state, to the next state, right? So this is TX data bit, right? So after the start bit, you need to do the data bit. So in that case, you need to update your state to TX data bit, right? So remember in the TX data bit, what we want to do, it's the same code as you see in, let me see, I believe in Lab 6. Let me see if I can find it. It's in the transmission, right? I think this is given to you, right? So it's actually over here. Okay, so this is the mask and transmission, but we can do it in a different way. Let's see. Just follow the logic here. So if mask is 0, what's going to happen? If mask 0, because what's the transmission function does is you are shifting the mask to the left, so the bit here, the 1 here to the left, and extracting every single bit from the byte, from the character. But whenever this one is shifted out to the left, it becomes 0, so which means you are done. All the characters in the byte is done. Okay, so in that case, if all the bytes are already shifted out, or all the bits are already extracted from the data, you wanna because for the UART, which means the last bit of the data is done. So the next step will be the stop bit, right? So you want to update the state to the TX stop bit. Okay, so which is the next. I'll just draw it here because I needed more space to write down more. Okay, TX stop bit. So that's the next state. So if it reaches this state, you want to move here and do a stop, whatever the stop bit has to do, right? But before we do that, let's see what else. So if mask 0, so else, right? Else, if it's not 0, it's not 0 yet. What you want to do? So all these steps has to follow whatever here, right? So I have to do the check, do the letter shift check, and then shift the mask and do the write, all this kind of stuff. Okay, because it's given, so I'm gonna leave this to you guys. So what's happening here is that you do the shift, you do the AND logic, and you do the extract, and you do the LED on and off, right? And you shift the mask. You shift the mask. Mask has to be shifted to the left by 1, because you have to shift this 1 to the left every single bit in order to extract every single bit from the byte. Okay, that's how that works. All right, so you need to do this, and then that covers all the conditions. For example, if max is 0, do this. If max is not 0, you keep shifting, right? Keep shifting, extracting all the bits from the byte. So What about this? If you are in a stop bit state, there will be different situations you have to analyze. For example, the first state is after this one, right? So it's all the bits has been received. Now you are waiting for a pull up to stop it. But the thing is, if you have this byte, received byte to be null, right? Then you wanna eventually just move to the next byte, which is the checksum. Then you are done. But if you are still at all the message bytes, you probably want to come back to start bit and receive another data, and keep shifting or keep detecting the next one. So it all depends on if the data being received from the transmit buffer. If this is this, right? If this is null, then what you want to do is go to a certain state. So which state you want to go to? Let's see. So if this is null, right? If this is null, you definitely pull it up for sure, right? Don't forget to pull it up. You're done. And you want to receive the next byte. So you want to go to start bit. So you can start the next byte, which is going to be checksum. So you want to have a flag. It's called checksum flag to be true. So next time it enters this stop bit, because this time still null, right? Still null, and the null is done. Null is done. So that's why it's equals to null. And then you transfer to the state to start bit. So eventually next time it enters interrupt, it's going to get in here and do the receiving and shifting, and it's going to receive and shift the check null, the checksum byte. So the checksum will be received and then enter into this stop bit. So since before that step you already set this to be true, so in that case yep, you want to use TX checksum. If TX checksum, which is flag, is true, so which means that in the previous interrupt it became true. So the next time, whenever checksum is transmitted, when it's reaching the stop bit, you want to enter here. The reason for that is after this one, you want to get it done. You don't want to do anything else anymore. So you are differentiating these two different bytes. So if it's already at checksum, checksum is done. That's why it enters here, and you want to directly go to idle because all the message is done. You don't have anything else. The state has to be idle, and the TX don't forget to reset it. Has to be false, right? Oh, sorry, correct right over here. And this covers one condition, the second condition, but also didn't cover the else, which is the normal cases. The normal cases will have to deal with all the normal bits, the bytes in the message. So the normal bytes in the message will also reach here, right? Reach here. Oh no, won't reach here because it's not null, right? So normal message will reach here, and the next time enters the interrupt, you just want to come back here to start another byte, right? Oh, state. Just update the state over here. Okay, and the transmit buffer, you need an index here, right? You need an index. So at the end, you don't want to forget to increment the index. The next time it's detecting. So you have the next one in the next byte in the transmit error buffer to be detected. All right, and this is pretty much all the states to be used for this state machine in ISR. And I may have missed let me see, maybe one or two things that I'm gonna let you guys to fill it up, but I can tell most of these are already the covers most of the major functionality of the ISR. Hopefully this will help you navigate this problem, right?